Hi, hello and welcome to another revision series on electromagnetic field theory and waves. So you can actually start with this third unit. You can see it is a very small unit and with very less number of topics. So we'll see the third unit. So let's get started. So you can see this is the first topic. We have Faraday's law, transformer EMF, inconsistency of Ampere's law, displacement current density. Then we have the Maxwell's equations in different forms, and the conditions at a boundary interface between dielectric and dielectric conductors. Okay, so we'll start with the first topic, that is the Faraday's law and transformer EMF. So this is the Faraday's law. So according to the Faraday's experiment, a static magnetic field cannot produce any current. But if there is a time varying electric field, it induces an electromotive force, that is EMF is induced in a closed path. Okay, so this EMF, it is the result of the varying magnetic field. So Faraday, what did he discover? That the induced EMF which is induced in the closed path, that is equal to the rate of change of magnetic flux linking with the current. So this is the statement form of Faraday's law. Faraday's law states that there is an induced EMF which is produced due to the rate of change of flux linkages. So this can be written in the equation form as E is equal to N into d phi by dt. Here N is the number of turns in the circuit and E is the induced EMF. d phi by dt is the rate of change of flux. So in the same equation, if there are only single turn is there, if the N is equal to 1, then this equation can be written as E is equal to d phi by dt. So this is the Faraday's law. Then we have the Lenz's law. Lenz's law, he postulated that the induced EMF, it acts in a direction so as to oppose the flux. So you can see the equation, the Faraday's law was modified by this Lenz. So according to Lenz, this is the equation, E is equal to minus d phi by dt. So this negative sign was given by this Lenz's law because the induced EMF acts in a direction so as to oppose the flux. So E is equal to minus d phi by dt. But we have an equation between the potential and the electric field intensity from electrostatics, which is E is equal to closed integral E dot dl. So in place of this, phi also can be written as integral of B dot ds, where B is the flux density. So in place of this phi, we can write minus d by dt integral B dot ds. And in E is also equal to closed integral E dot dl. So equate both of these two. So closed integral of E dot dl is equal to minus d by dt B dot ds. So now take this differential term inside the integral. So we can write it as minus dou b by dou t dot ds. So if you see, this is similar to the transformer action. That's why this EMF is known as transformer EMF. Therefore closed line integral of E dot dl is equal to minus dou b by dou t dot ds. Now we have a theorem known as Stokes theorem. So according to the Stokes theorem, a closed line integral can be converted to a surface integral. So this is the equation form. E dot dl, closed integral of E dot dl is equal to del cross E dot ds. So in place of this left hand side, we can write del cross E dot ds. Del cross E dot ds integral, this is equal to my integral of minus dou b by dou t dot ds. Or equate the like terms on both sides. We have the integral, we have the dot ds term. So if you remove these terms, these are the terms left. Del cross E is equal to minus dou b by dou t. This is one of the Maxwell's equation. But if the magnetic field is not varying with time, so we can take this term as 0. Dou b by dou t is equal to 0. Therefore, closed integral E dot dl is equal to 0. Or del cross E is also equal to 0. So this is the derivation for transformer EMF. Next we have the generator EMF. So in the previous case we have taken that the magnetic field was time varying. So in the generator EMF, the magnetic field is stationary and the closed circuit is revolved or rotated to get the relative motion between them. So if you observe, this is an action which is similar to the generator action. That's why this induced EMF, we also call it as the generator EMF. Here we have a small derivation. If you consider a charge Q which is moved in a magnetic field B with a velocity of V. Okay, so this V is the velocity of the moving charge. Then the force acting on this charge can be written as F is equal to QV cross B. Here Q is the charge, V is the velocity of the moving charge, and B is the magnetic flux density. But in electrostatics we have the relation for electric field intensity, which is equal to force per unit charge. So in place of F we can substitute QV cross B divided by Q. If you cancel Q and Q, we get V cross B. So the induced EMF, closed integral of EM dot dl is equal to closed integral of V cross B dot dl. Now if the flux density is also time varying, then the total EMF is the combination of the transformer EMF and the generator EMF. So you can put both of these terms. This is the transformer EMF term and this is the generator EMF term. So the total induced EMF is the combination of the transformer EMF and the generator EMF. So this is all about the transformer EMF, Faraday's law and generator EMF. The next topic we have, this is the inconsistency of Ampere's law. Now this equation we come across in the magnetostatics. So according to Ampere's law, we have this equation del cross H is equal to J. Now if you apply divergence on both sides, so divergence is applying this del dot. Put del dot on left side and right side. Del dot del cross H is equal to del dot J. But this is the divergence, and if you see this term inside the brackets, del cross H. This del cross H is the curl of H. But the divergence of the curl of a vector is equal to 0. Therefore we can write this as del dot del cross H is equal to del dot J. So this is equal to 0. Now we have a continuity equation which is del dot J is equal to minus dou rho V by dou T. So equate this to 0. Here we have del dot J is equal to 0. So we can write del dot J is equal to minus dou rho V by dou T. This is also equal to 0. Now if you say this equation, we can observe that it is not compatible for time varying fields. So what does this mean here? If you see this dou by dou T of rho V, here rho V is the volume charge. So if the volume charge is not time varying charge, here we are getting it equal to 0. But actually the volume charge which is time varying, it is not equal to 0. That means this is not compatible for time varying fields. So this equation has to be modified for time varying fields. So this is the inconsistency of Ampere's circuital law, and this was rectified by Maxwell again. So this was from here, it was done by Maxwell. So this equation has to be modified for time varying fields. So we can remodify this equation and write del cross H is equal to J plus N. Earlier it was only del cross H is equal to J. Now take another term here, J plus N. Now apply divergence on both sides. Del dot del cross H is equal to del dot J plus del dot N. But divergence of curl is equal to 0. And we also have this continuity equation, del dot J is equal to minus dou rho V by dou T. So in place of this del dot J, substitute minus dou rho V by dou T plus del dot N is equal to 0. Or take this term towards the right side, we get del dot N is equal to dou rho V by dou T. Okay, but according to Gauss law, we have this equation, del dot D is equal to rho V. So in place of this rho V, we can write del dot D. Therefore, del dot N is equal to dou by dou T into del dot D. Or you can arrange this properly and write del dot dou D by dou T. So del dot N is equal to del dot dou D by dou T. So equate the similar terms on both sides. We can write N is equal to dou D by dou T. Now we can write the modified Ampere's circuital law as del cross H is equal to JC plus dou D by dou T, because in here we got N, the value of N as dou D by dou T. Now here this first term, that is the conduction current density, and the second term, that is the current density expressed in amperes per meter square, which is also known as the displacement current density. Another name for this is the convection current density. Okay, so this current density exists in dielectrics or insulators. So this is the modified Ampere's circuital law, which is this one, del cross H is equal to JC plus JD. Here JC is the conduction current density and JD is the displacement current density. So this is the expression for the inconsistency of Ampere's circuital law and the modified Ampere's circuital law. The next topic we have is the Maxwell's equations. So Maxwell's equations in differential form and integral form. So point form or in differential form. These are the two forms of Maxwell's equations. One is the point form or the differential form, and the second one is the integral form. So these are the four Maxwell's equations in differential form and integral form. See the first one, we have del cross E is equal to minus dou B by dou T, and del cross H is equal to J plus dou D by dou T, del dot D is equal to rho V, and del dot B is equal to 0. So the same equations in integral form can be written like this, closed integral of E dot dl is equal to minus integral dou B by dou T dot ds. This is the Faraday's law, that is the transformer EMF. Then we have the second equation, closed integral of H dot dl is equal to J plus integral dou D by dou T dot ds. Again, this is the Ampere's circuital law, that is a modified form of the Ampere's circuital law. Then we have the Gauss law in integral form, closed integral of D dot ds is equal to rho V. Then the last equation is closed integral of B dot ds is equal to 0. So this equation represents that there is no isolated magnetic charge, that is the magnetic charges always exist in pairs. That is there should be always a north pole and south pole, not an isolated north pole or not an isolated south pole. So these are the four Maxwell's equations in differential and integral forms. The next topic we have here is this one, the conditions at a boundary interface. So we'll see what are these conditions at a boundary interface. So what is meant by this boundary interface or boundary surface? So whenever electromagnetic wave is passing through any medium or any through free space, so it has two components. One is the electric component, second one is the magnetic component. So the electric component, again it has two more components. One is the tangential component, second one is the normal components. The tangential component we can denote it as ET, and the normal component can be denoted as EN. Now whenever this electric field is moving in any dielectric medium or free space or any conductor, then what the boundary between the two media, it has some effect on the electric field and its components, and the study of these effects existing across the boundary, these are known as the boundary conditions. So first we'll solve the boundary conditions at a dielectric interface. Now if you see this diagram, we are taking two dielectrics. One is the dielectric 1, that is region 1, and dielectric 2 is region 2. So here we'll consider the two components of electric field. One is the normal component, second one is the tangential component. So as both are dielectrics, both of them will be having permittivities. So we'll consider the permittivity of the first dielectric as epsilon 1, and the permittivity of the second dielectric is epsilon 2. The electric field intensity and the electric flux density have both the components, that is the tangential components and normal components. So E can be written as sum of the tangential component and normal component, that is E is equal to ET plus EN. Similarly, D is also equal to DT plus DN. So here we will consider a closed loop between at the boundary in these two dielectrics, the boundary between these two dielectrics, the region between A to B, B to C, the path between A to B, B to C, C to D, and again D to A. Now we can start with this equation, that is the potential in a closed loop, closed line integral of E dot dl is equal to 0. So we'll consider the distance between A to B as delta W, C to D is also delta W, the distance from B to C is delta H, and A to D is also equal to delta H. So between B and the boundary, we'll consider it as half of this delta H, that is delta H by 2. And another one between the boundary and to C, that is the distance between the boundary and C, that we also consider as delta H by 2, half of this delta H. Similarly this side also, between A to boundary, that is half of delta H, that is delta H by 2, from boundary to D also, that is delta H by 2. Now we have to remember one important point here. Whenever the field is entering the boundary or whenever the field is going to the boundary, that has to be considered as a positive value, and when the field is going away from the boundary, then it has to be taken as a negative value. Now we'll use this equation, we'll apply this equation for this closed loop A, B, C, D, A. So we'll start with this from A to B. Between A to B, it is the tangential component, and it is a tangential component of dielectric 1. So we'll write it as ET1 into the distance between A to B is delta W. Then between B to the boundary, that is the normal component of electric field. As it is region 1, we'll denote this as EN1. And the distance from B to the boundary, that is half of the delta H, that is delta H by 2. As this field is entering the boundary, we have to consider it as plus. Next, the path from the boundary to the point C. Now here the field is moving away from the boundary, so put a negative value here, minus EN2. EN2 because it is in the region 2 and the distance is delta H by 2. Next, from C to D. From C to D, the field is in the opposite direction as A to B. Like suppose if we are considered from A to B, if you see the direction of field from C to D, it is in the opposite direction. So that's why we need to put minus ET2. 2, why? Because it is in the region 2 and the ET2 is a tangential component. And the distance between C to D is delta W. Next, the path from D to this boundary, this small path. So it is entering this field here, it is entering the boundary. So we need to write a plus value. And it is in the second medium, so write EN2. And the distance is delta H by 2. Next, from the boundary to A. So this field is going away from the boundary. So we need to put a minus here, EN1, because it is in the region 1 and the distance is delta H by 2. So equate this to 0. Now these two terms are cancelled, plus EN1 delta H by 2 and minus EN1 delta H by 2. And minus EN2 delta H by 2 and plus EN2 delta H by 2. So these four terms get cancelled. So these are the terms left. ET1 delta W minus ET2 delta W is equal to 0. So from this equation we get ET1 is equal to ET2. So from this equation we can conclude that the tangential component of electric field is same or continuous at a dielectric interface. Next we need to solve for the tangential components of D, that is the electric flux density. So for doing this we can use the relationship between D and E. So D is equal to epsilon into E, or epsilon can be expanded as epsilon naught and epsilon R into E. So to find dt1 we can write epsilon naught epsilon R1 into ET1. Similarly, to find dt2 we can write epsilon naught epsilon R2 into ET2. So from both of these two equations we can observe that dt1 is not equal to dt2. So this can be written in the statement form as the tangential component of D is not same or continuous at a dielectric interface. So till now we have solved the tangential components of E and D. Next we need to solve for the normal components. So to solve for the normal components we will apply the Gauss law. So for Gauss law we need to take a surface. So here we will take a cylindrical surface between two dielectrics. Dielectric 1 is the region 1 and dielectric 2 is the region 2. So we will apply the Gauss law here. So for a surface the charge Q can be written as integral rho s into ds. Or if this ds is integrated we get rho s into s. So if you take the differential terms we can write delta Q is equal to rho s into delta s. So this we can expand it as dn1 delta s minus dn2 delta s. So why negative? Because the flux leaving the top and the bottom surfaces is the difference of both of these two fluxes. So equate this with rho s into delta s, or dn1 minus dn2 is equal to rho s. So here both the material or the media are the dielectrics. So for a dielectric there is no surface charge. So we can write rho s is equal to 0, or dn1 minus dn2 is equal to 0, or dn1 is equal to dn2. So this we can write in statement form. That is the normal component of D is continuous at a dielectric interface. Next we need to solve for the normal components of E. Again we can use the same relation between D and E, where D is equal to epsilon into E, or E is equal to D by epsilon. So En1 is equal to dN1 by epsilon naught epsilon R1, and En2 is equal to dN2 by epsilon naught epsilon R2. So from both of these two equations we can see that En1 and En2 are not the same. So we can write this in statement form, that the normal component of electric field is not equal or continuous at a dielectric interface. So we need to solve the similar equations for conductor dielectric interface also. Here also we start with the same equation, closed integral E dot dl is equal to 0. Again consider the same path between both of these two materials. In the earlier case we have considered both dielectric materials, but now here media 1 is a conductor and media 2 is a dielectric. The rules for writing this expanding and writing this equation is the same. So start with ET1 delta W, that is a tangential component, then the normal component En1 delta H by 2 between these 2 points. Next from here till here it is minus En2 delta H by 2. Next from C to D it can be written as minus ET2 delta W. From D to the boundary plus En2 delta H by 2, and from the boundary to A write it as minus En1 delta H by 2 and equate it to 0. Here also we get the same thing, ET1 delta W minus ET2 delta W is equal to 0, or ET1 is equal to ET2. But if you see, there is no charge inside a conductor. That means the charge inside a conductor is equal to 0. Why? Because the charge is present only on the surface of the conductor. Therefore ET1 is equal to 0. So in this equation substitute ET1 is equal to 0. Therefore we also get this ET2 equal to 0. So we can conclude this as that the tangential component of electric field is 0 at a conductor dielectric interface. Next we need to solve for the tangential components of D by using the relation between D and E. dt1 is equal to epsilon naught epsilon R1 ET1, but ET1 is equal to 0, therefore dt1 is also equal to 0. So here also ET2 equal to 0, therefore dt2 is also equal to 0. So here also you can conclude that the tangential component of D is 0 at a conductor dielectric interface. Next, to solve the normal components, we apply the Gauss law, where Q is equal to D dot ds, which is also equal to rho s into ds. So integrate this ds, we get rho s into s. Again put the delta terms here. Delta Q is equal to rho s delta s, and delta Q is also equal to dN1 delta s minus dN2 delta s. So equate this with delta s into rho s into delta s. So we get dN1 minus dN2 is equal to rho s. But dN1, if here we have considered the conductor as the material 1 or medium 1, but dN1 is equal to 0 because there is no flux inside a conductor. So put 0 in place of this dN1. So we get dN2 is equal to rho s. Next we need to solve for normal components of E by using the relation between D and E. E is equal to D by epsilon, but En1 is equal to 0. So En2 is equal to dN2 by epsilon naught epsilon R2, but dN2 we got it as rho s, so in place of dN2 write rho s by epsilon naught epsilon R2. So we can write this in statement form. Hence the normal component of D is equal to the surface charge density, and the normal component of E is proportional to the surface charge density. So these are all the topics in this unit. Sometimes in the exam this is also expected, to derive the conditions at a boundary interface between conductor and free space. So here also we do the same equations. Start with the same equation, E dot dl is equal to 0. This expansion is also the same. So for a conductor there will be no field inside the conductor, so that terms can be made zeros. So E and D will be zeros inside a conductor. So here we have taken the top material media as free space and the bottom one is a conductor. So ET2 and DT2 both will be zeros. So use this equation, ET1 minus ET2 equal to 0, but ET2 is equal to 0, therefore we get ET1 is also equal to 0. Similarly, you can calculate the tangential components of D by using the relation between D and E. So we get both of these two terms are also equal to zeros. So the tangential components of D are 0 at a conductor free space interface. Next, to solve the normal components, again we use the same Gauss law. Start with the Gauss law and use the equation delta Q is equal to dN1 delta S minus dN2 delta S equal to rho S into delta S. But here dN2 will be equal to 0, that is there is no flux inside a conductor. So put 0 in place of dN2. So we get dN1 is equal to rho S, that is the normal component of electric flux density is equal to the surface charge. Next we need to solve the normal components of E by using the relationship between E and D. So we get En1 is equal to dN1 by epsilon naught and En2 is equal to dN2 by epsilon naught epsilon R. Now here En2, this is a dielectric conductor, so we need to write dN2 by epsilon naught epsilon R. But if you see the top material or the media, that is free space, so in place of epsilon we need to write only epsilon naught. So this is the equation, En1 is equal to dN1 by epsilon naught. So these are all the topics in this unit. So this is actually very small unit. So first learn this one, then you can go to the other units. I hope I am clear, and thank you for watching.